Welcome. In this session in linear data analysis, we'll explore how we can project a given vector to a two-dimensional vector space. So now, let's suppose that let's consider a vector space V, and let's suppose that we have a basis for it, which is a first vector and a second vector, both A. So if they're basis vectors, that means that they're both non-zero and that they are not linearly dependent, which means that they're not scalar multiples of each other. Suppose we are given a new vector C, and the question is, what vector P, what projection vector that's in the space spanned by these two is nearest to the given vector? And there are a number of ways that we can do this. Let's draw a picture first. Let's suppose that our given vectors look something like this. This is A1 and this is A2. And suppose that we are given a vector which is some vector C. And that vector C will, what we want to do is we want to project it, or we want to have an orthogonal projection to some vector P that is in the vector space spanned by A1 and A2. So P is some linear combination of A1 and A2. And as before, what we'll do is we'll construct an error vector that is the difference between this given vector C and our desired vector P. So if that's our picture, what algebra corresponds to it? Well, now what we'll do is we'll define our projection, which is in the vector space V. So that means it has to be a linear combination of vector 1 and basis 1 and basis 2. So that means that if I take basis vector A1, that there is some weight or scalar multiple of it, and then I take basis vector 2 and I add some other scalar multiple, and that those have to add up. Well, one of my general rules in linear algebra is when I see a bunch of numbers, I gather them into a vector. And here I see W1 and W2, and I naturally want to gather those into a vector. So how could I write P? Well, I could write P as being W1, W2. Now, another one of my rules is when I see a bunch of vectors, I try to gather those into a matrix. How could I gather these? Well, to get P, what is W1 multiplying or multiplied by? Well, that would be A1. And what is W2 multiplied by? Well, that would be A2. So I can write the projection vector as a matrix. Remember, we don't know the size of A. A could be really, really long, right? But it's some matrix times a vector of size 2. So I can write that as a matrix A times a vector W. And then I'll do the same thing as before. I'll define my error vector. I'll define that as being the given vector C minus the vector P. So that is as we did in one dimension, and that corresponds to our diagram that we're working from. So now, what do we have? Well, now we have this requirement. So E must be orthogonal to vector A1, and E must be orthogonal to vector A2. Why? Because if it wasn't orthogonal, then that means that it would have a longer length, right? So what we're basically doing is we're arguing geometrically that if I vary E around, I'll find out that it has to be perpendicular to both. So let's write these in linear algebra. Well, as before, what that means is that this is a pair of constraints. So we could write this as A1 dot E equals 0. And we could also write A2 dot E equals 0. Now, I see two equations and I see some commonality. Can I gather that into, so now I see these dot products, right? So the next thing I want to do is I want to say, turn those into transposes so that I can do some easier manipulation. So I will turn those into transposes, and now I see two equations and they share some commonalities. So now let's gather these again. Let's do another big gathering. And let's check that that is the same as A1 transpose A2 transpose times E equals 0, 0. So that's what I think. Let me cross-check. That would be A1 transpose E, so that's a scalar, equals the first entry. A2 transpose E is the second. Can I rewrite that? Well, yes. What relationship does this matrix have to this matrix? Yeah, it's the transpose. So that means our constraint is that A transpose E equals, and what's that? That's the 0 vector. We'll solve this in the next session. Right now, let's pause and make some observations. So let's observe that that means that E is in the null space of A transpose. Why? Well, it has to be because what we're saying is that that error vector, when transformed by A transpose, is the 0 vector. And that's the very definition of a vector being in the null space. Well, we can also say that E is in the orthogonal complement of V. And why is that? Because if a vector is in the null space of the transpose, that means the vector is unreachable in the original one. And if you want to, you could use the SVD and you could show all of this has to be true. So we won't go through that SVD, but what we'll observe is that A transpose E equals 0 that's our constraint equation. That means that the error vector must be in the orthogonal complement of V. What does that mean geometrically? Well, that's exactly what we mean, is that the vector space V is some 2D space in some m-dimensional coordinate space. So whatever that bigger coordinate space is, let's imagine that it's 3, okay? That if we say that this is a 3D picture, then the vector space V that has a basis of 2 of these is a plane in a 3D space that includes the origin, because that's the definition. And what we're saying is that E has to be completely perpendicular to that. And that is a geometrical interpretation of it being the orthogonal complement. Of course, once we get into a larger size, 4, 5, 20, it's not uncommon in my research for me to deal with 1,000-dimensional vector spaces. And in those cases, my imagination is insufficient, and I'm reduced to statements in linear algebra such as this.